Yes, please. Yes.
Okay. This call is now being recorded. So, welcome to all the participants, and welcome to you, sir. Also, this is the third day and third session. This session will be taken care by Dr. Sunil Kumar Mishra. Please join me to introduce him, the speaker, to all the participants. Dr. Sunil Kumar Mishra is an assistant professor in the Department of Physics at Indian Institute of Technology, that is IIT BHU, Varanasi. Dr. Mishra has completed his PhD in 2011 from the Department of Physics from IIT Kanpur and MSc in 2003 from RML Awadh University, Faizabad. His research area of interest includes quantum information and computing, quantum entanglement, frustrated magnets, etc. Dr. Mishra owes a significant applause for his research contribution in his research area, which includes many distinguished publications. Dr. Mishra has several years of experience in teaching and research since 2010. With this brief introduction, I'd take this privilege to invite you, sir, and hand over the session to you. Sir, please.
Thank you, Dr. Jayanta. And I'm glad to be here among the colleagues, and would we like to present some recent work and the directions, because as I think that most of you are trying to enter in this domain in the quantum computation, quantum teleportation. So I will try to be as simple as I can, and you are free to interrupt me in between. Okay, I'll be ready to take questions. And yeah, so let me make a full screen and then start. Okay, so yeah, so the topic of my talk is today is quantum teleportation using spin chains. And I will try to introduce you bit by bit what actually we mean by this, what we supposed to do when we finish the slides. I hope you will get a feeling of using this quantum teleportation in some actual setups, in fact, some realistic setups also. And in fact, the most important thing is that the system that we will be dealing at the end of this talk, that will be a condenser systems, and applying this quantum information knowledge to that system. Okay. So as Dr. Paul introduced me, that I work in IIT BHU, Varanasi, and my most of the research now is focused mostly in quantum computing direction, with preparing this quantum states with ways like data efficacy diamonds, and trying to understand more on the quantum information aspects, the processing aspects. One of the aspects is this quantum teleportation. Okay. And mostly we deal with the condenser systems like spin systems. So as I progress, I will try to inform you about this basics of this quantum computing, in fact, quantum information. We will start discussing about the qubits, and then I will discuss about this a bit on this gates, quantum gates, and then we'll move to this quantum teleportation protocol, that standard protocol that was given by long time ago, none other than Charles Bennett and the team. And then we will tell you about more about with the spin chain. I hope the diverse audience, probably most of you have not had gone through this topic, the information system. So I will try to briefly introduce the spin chains, and then we employ this concept of teleportation on these spin systems. Yeah. So spin is actually the internal degree of freedom of the system, which you don't have, like you don't have a classical counterpart of spin half, and even a classical top, that is spin top, is not a spin, because when you see the first experiment that is done by Stern and Gerlach in 1922, that when this let's say you consider some atoms which only have which are not having this orbital momentum, and if they pass through some setup which has a non-uniform magnetic field, which is just directing, let's say, in one particular direction, and what you see on the screen one gets two spots. rather than one circular spots that was predicted earlier, that the outer momentum is total computation coming to zero, then there should be no deflection and one should get a bright spots on the screen. But what we get actually are two spots. And if we change the locations of this this magnetic field directions, no matter what direction you take, you get two spots. And that quantization is earlier thought of as a space quantization, and later it's a fundamental of quantum mechanics, and it should be there that whenever you deal a quantum particle, we have to talk in terms of the spins also. So all these spins, like the electrons, photons, okay, all these systems, whether they have some spin number is there. For some it is integer spins, and for some it is this in half integer spins, and they rotate in the space such that if you do a 2-pi rotation, you won't get the same state, but you need to do a 4-pi rotation to get this retrieval of the state. So the calculations, the understanding with the spin halves is more important because they are the smallest dimension systems. They have Hilbert state dimension of 2, which means that you have only two levels. One has you can consider as a down level and one as an up level, and there's a gap between these two levels. And that makes it interesting. One can say it as a most quantum system because the quantum mechanics, one can understand quantum mechanics more appropriate way when you deal with these two state systems. Okay, the quantum, because if you take more and more number of levels increased, then you will slightly move toward the classical system. And in fact, if you have some system has, let's say, 100 levels, then it's a more probably it's a better prepared described by a classical system rather than a quantum system. So the number of levels decreasing, the system is more and more quantum, and this is the smallest possible dimension in a Hilbert space that a particle could have, and that's why the interest with spin halves is more than any other systems in quantum computing. And what is more surprising is that our definition of bits in classical domain, we define like some 0 or 1, the indices, which you can just flip. Maybe it's a digital signature. You can 0, you can take on, off for the states, and one has a correspondence with this eigenstates of this spin half matrix, the operator. Okay, we call this as polymetrics. Okay, and the eigenstates are actually have two states to be there because it's a Hilbert space dimension is 2. So one, that is the up spin pointed, we call it a 0 level. And remember that the 0 inside is like a classical bit is there, and the angular brackets that we put there, the Dirac ket, okay, that makes a quantum system. Okay, so unlike a classical bit, you have a 1 person. Here you have a column matrix there that is representing this 0 level. Okay, 0 level is 1 0, and similarly this 1 level is 0 1. Another this column matrix. Okay, and together they form a quantum bit. And whatever we understanding of quantum computers to be done will be based on these 2 bits. We call it quantum bits. Okay, and whatever be this development is going on from last we can say 50 years in this domain, it's mostly focused on this quantum bits, qubits, which are realized by the eigenstates of a spin half. Okay, the system can be like, you can have electrons, as I pointed out earlier. You can have other systems, some solid state systems. For example, nitrogen vacancy centers in diamond, they are also nowadays very good this qubit candidate. There are also superconducting qubit states. Okay, people used to realize them, and Josephson-Jackson qubits. Okay, lots of the things going on in this direction to realize the portable setup, and which not only have a portability into account, but also robustness is into account. That means that the state of the system that you take with whatever qubit you find, the state you define, that state should remain for at least like some it should have the coherency is there, that it's not decohered by the environment or by some other aspects, or it maintains what you call up. It maintains up for a longer time, or during the experiment period, or during the calculation period. Okay, so lots of advances going on by preparing these states, qubit states, and understanding their dynamics. Okay, so we are not going to much towards this preparation the aspects. Okay, but we will be mostly using the utilization aspects of this quantum bits. So the quantum bits usually quantum bit, if you consider, it's for one spin half, and its projections can be considered as the projections on a Bloch sphere. Any unknown qubit you can define as any point in this Bloch sphere. Okay, so by the time, this means that if I need to choose this A and B parameters, define any unknown quantum bit. Okay, so this actually has you need to do infinite ways, because this A, if you choose any point on this surface of this sphere, Bloch sphere, and B to be any point on the surface of the Bloch sphere, they are equally good candidate for a qubit. Okay, so there is infinite ways in this to generate this qubit, because A and B parameters, they are real numbers lying on this surface of the sphere. Okay, with the condition that mod A square plus mod B square equal to 1. And it is always good to call them, because in this way, quantum mechanics works like a superposition state, because psi, you see this state, that is like a superposition state of two qubits, 0 qubit and 1 qubit, with a weight A for 0 qubit and with a weight B for the 1 qubit. That means probability of finding this qubit in 0 state is mod A square, and probability of finding this qubit in 1 state is mod B square. Okay, so 0 and 1, they are called as a basis for this n equal to 2 dimensional space, and it is not unique basis. You would have other choices also, because you have infinite choices up there to take a basis. Okay, and that means that what you call 0, what you call 1, okay, it is the particular choice of the basis. If you take a polymetric sigma x and calculate its eigenvalues and eigenstates, you get again eigenvalues will be 2 eigenvalues plus 1 minus 1, and the corresponding 2 eigenstates will be there. Okay, so what we are calling this, it's independent of what you choose a basis. You can define a qubit on a Bloch sphere, but the convention usually is taken as to take a polymetric sigma z and its eigenstates to define a qubit. So this 1 qubit system you can represent on a Bloch sphere, but if you deal with a 2 qubit system, you cannot define on a Bloch sphere. Okay, because there are two separate things are there. Okay, but one can define this states, this 2 qubit states, the joint state. One should always keep in mind that when you define this 2 qubit space, that means that 1 qubit belongs to a Hilbert space of the first qubit, and the second qubit belongs to the Hilbert space of the other qubit. Okay, that's how we can write for any joint state. We can write as a product space. This product of, let's say, I call A space, the qubits are there, and the product space of B space qubit. Okay, so this we can define as joint state. Okay, if we find that a joint state is just as a product of these two states, okay, then we call it it's entangled, it's unentangled, because if you remove this one part, it is like nothing is affected on this second part. Okay, however, if we cannot write a joint state of the two spin systems like a product space, that means there is an entanglement involved there. That means there is some information is there, that if you try to pull out one of the system, the content of the missing information is always there, is already there for this joint system. Okay, so you cannot write in the product space if the pair of spins, they are entangled. Okay, for instance, this you have four pairs, known as Bell pairs. They are written like a 0A. You can see that 0A cross 1B minus 1A cross 0B. If you try to extract one of this spin, let's say A part you try to extract out, okay, what you get actually is a mixed state. That's the identity. Okay, that means you don't get any, you don't separate it out A part. Okay, they are so much mixed that if you try to pull out one part, you get a mixed state. You get information that there is something that is missing there. Okay, but here if you pull out A part, this remaining part is a pure state, and one can do analysis. You can say because these are unentangled states. Okay, there are four such kind of objects for a 2 qubit system. Okay, and they are maximally entangled because if you try to quantify the entanglement in some way, there are various ways to quantify entanglement. For example, one can calculate concurrences, one can calculate fundamental entropy, one can calculate some other measures like negativity, partial PPT transpose. Okay, and all those measures, they will just categorize this quality of this kind of states, that they have a maximum entanglement possible for a 2-qubit system. Okay, in fact, one can always define this states, like if you want to quantify entanglement, okay, because this is such maximum entangled states, so whatever the configuration should be there, their entanglement should be 1. Okay, and whatever be other states, they will always be lesser entangled than this 4 Bell pairs. Okay, so there are not only this 2-spin system, one can go for the highest dimensions, one can increase this number of spins. Okay, and one can write this product space, and if you cannot write the product space, that means there is an entanglement involved. Okay, and you actually, when you have many parties involved, then you actually have a many party entanglement, because you got a multi-partite entanglement. However, in these 2 parties, there's only 2 parties involved, A and B, then the entanglement content is like a bipartite entanglement. Okay, even in the multi-partite system also, you can define the 2 parties, and then one can calculate bipartite entanglement by defining some blocks of this 2 blocks of these spins, and one block you can separate it out, other block you can do calculations. Okay, separating out one block is called as a partial trace in quantum mechanics. Okay, so when you do this partial tracing, for example, the Hilbert space dimension in this case for the 2-spin systems is not n is equal to 2, but is a 4 by 4. Okay, and when you try to do a partial tracing, okay, you want to know only one block of this system. Okay, then this will be dimension will reduce to a 2 by 2, and you do it systematically, so that this the other basis that is removed there, and you get this system of this B space. So definitely, like you get it. There are lots of work going on maximally entangled this multi-partite entanglement. Okay, how to quantify them. Bipartite entanglement is literally like well understood things are there, and one has lots of understanding in terms of this measures, their behavior. Okay, the systems. Okay, however, the many party systems are less explored, and lots of work going on to how to quantify. For example, one uses quantum physical information to quantify this multi-party sharing involved there, which is more than this bipartite sharing. Okay, all those things are going on. So again, we are not focusing in that direction. Okay, and but definitely there are lots of interesting grounds there also. If one wishes to explore there, the multi-partite entanglement, there is lots of interest there. There are lots of games designed for multi-partite sharing. Okay, one can understand those things. And yeah, so basic building block of this the quantum computing, the quantum computer is the quantum states we discussed right now. And the other thing is this the gates. Just like in classical computing, you have this classical bits and classical logic gates are there, and you perform the operations there. Operations means this classical state, the bits, they transform in some way and give you some required this manipulated results. When you want to calculate addition, you want to subtract, you want to do multiplication, you want to do whatever, you want half adder, full adder, whatever you want to do, you can do there. The same way you can do with the quantum bits also, with the help of quantum gates. Okay, and in quantum mechanics, what is important thing is there that you don't do any ordinary transformations. You always have to go through a unitary way. The transformation that you provide in quantum mechanics, in quantum computing, the transformations are unitary. That means if I have this X, this matrix is there. Okay, so if I take this X transpose, okay, that's will be equal to the inverse of this X. Okay, this is fundamental rule is there that in quantum computing, the gates that you are taking, they should be unitary. Okay, what is unitarity is gives you in the fact that, let's say you propagate the system from some t equal to 0, so some time t equal to t by some unitary transformation. Okay, you can always have the inverse of this transformation. Okay, to get it back. Okay, so this is kind of the reversibility is offered by this unitary evolution. Okay, unitary transformations, they provide you reversibility. Okay, unlike this non-unitary gates, where you don't have reversibility into hand. Okay. So there are a few important gates in this domain. Okay, single qubit gates which actually act on single qubits. For example, this is a very popular gate, X gate, that is kind of a NOT gate for the quantum computers. Okay, where any qubit you put as an input state, and what you get is a inverted. This side tilde you get. Okay, side tilde, the action is such that this X is like a poly X matrix, and this poly X matrix when acts on this states, for example, it acts on 0, it inverts it to 1, and when it acts on 1, it inverts it to 0. Okay, so it's just like a NOT operation there in classical computing. Okay, this X gate is sufficient enough to provide you the NOT operation in quantum computers. There is another gate, Z gate is there, that is also very useful gate there. It just picks a phase there. Okay, when you apply this on any state, input state A, it just picks up a phase e power I by A. And remember that A is a qubit is there. Okay, so it has a possibility either 0 or 1. So if you put exponential I by 0, it is 1. If you put exponential I by 1, it is -1. Okay, so correspondingly, when Z acts on 0, it gives you 0 gate. When Z acts on 1, it gives you -1 gate. And this is, the polymatrices are unitary, they are Hermitian, they are unitary. If you take square of the polymatrices, you get identity. That justifies you that they should have two eigenvalues, +1, -1. Okay, lots of algebra you can do with the polymatrices. So X and Z, the good polymatrices, they act as a very good gates in quantum computers. One like a NOT gate, and one picks up the phase. If 0 is there, no change. If 1 is there, this gate will put a minus sign. It will identify if it is 0 is there, or if it is 1 is there. Okay. There is one more very important gate is there, that is called Hadamard gate. Okay. Hadamard gate is usually used that it just provides you, just gives a basis transformation. Like if you have this Hadamard gate in terms of matrices, it is like a 1/√2, 1, 1, -1. And when you apply it on 0 gate, it will give you 1 by square root 0 plus 1, which is nothing but eigenstate of sigma x. Similarly, Hadamard gate acting on 1, that is eigenstate of sigma z, it gives 1/√2 0 -1, the eigenstate of sigma x again with the -1 eigenvalue. Okay. For example, we represent a block sphere. When Hadamard gate acts on 0, this 0 gate, it returns to this state. The orientation of this gate is changed. Now it is not in Z direction, but it is X direction eigenstate. Okay. Similarly, when I act this Hadamard gate on this one gate, the orientation changed to 0 -1/√2. Okay. So under the application of Hadamard gate, this axis Z changes to X axis. Okay. And you do successively one more Hadamard operation you apply, then you get the state back. Okay. So you guarantee, because Hadamard square is again identity, that means nothing has been done on this state if you apply successive Hadamard operators there. So we'll be using this Hadamard gate many times. In fact, they with the action of this other the gate, the 2-qubit gate. Okay, they in fact give you the Bell states if you act carefully. Okay, so there's one more gate is there that is very important in quantum computing, is the C0 gate. Okay, which actually is doing like it is there's a 2 bits are there. The dot one is called this control, and this where you have this tensor addition is there, that is called as a target qubit. Okay, so when you have two qubits passes through this C0 gate. Okay, so nothing happens to the one which is passing through this control, but the target one will switch, such that this sign means that you have to take A plus B divided by 2 and the remainder that is there. If it is 0, then it is 0. It is 1, then it is 1. So that means whenever the B is going to 1, definitely you get the remainder that is different. Okay, so it flips whenever B is 1. it does nothing when B is 0. Okay. So sorry. Yeah. So it just have this target. This control is there. When control is 1, it flips B. Okay. If control is 0, it doesn't do anything. So under the C naught operation, if you have 2 qubits 0 0, they will transform to 0 0 because control is 0. So nothing will happen to target. If you have a 0 1 state, the control is 0, target is 1, nothing will happen because control is 0. But if control is 1, then target is going to flip. It is now 1 1. Okay. And if control is 1 here again, the target is going to flip. It's going to 1 0. Okay. So if someone trying to ask some question there in between, so I may not be able to. You can just inform me. Okay. I thought maybe something clicked, so maybe I thought someone asking questions. Yeah. Yeah. So that's it. So these two single qubit gates, this X, Z, H, together with C naught gate, they are like universal gates, and you can do all tasks. You can make whatever the task there with the help of these two gates. Okay. There are also the 3 qubit gates that we do not listen. The Foley gates and swap gate is there. Okay. But all the actions one can, they're like at a minimum building block for a quantum computer. If you can prepare a single qubit gate and you can prepare 2 qubit gates. In experiments, usually, for example, in NMR experiments, the pi pulses are some way. Okay. These gates one can construct there and you can do calculations there. But again, I say that we are not there. These gates can be realized by experiments, but we are not going to direction of the realization aspects now. Okay, so we will be mostly dealing with the computational aspects. Yeah. Okay, so that's now we are going to move with this slight appetizer of this fundamentals of this quantum computer. We are moving to the main topic of this discussion, that is quantum deliberation. And this is defined as a strategy that you will use with local quantum operations and classical communication, that you can use a classical signal to talk. There's a telephone is there. It's just a representation for a classical talk. And the local operations, that these two sites, two labs, Alice and Bob's lab, they can do local operations on their side. Okay. And what they do in the process is that any unknown qubit, okay, this is unknown because if you try to measure it, then it will be known qubit. So you don't measure it. Let's say alpha 0 plus beta 1 is a known qubit is there. And this unknown qubit, Alice wants to send it to Bob. It is kind of information. Okay. It is kind of information that she can have, alpha and beta have infinite choices there. Okay, if she is not playing with if the state is unknown base, then alpha beta can be encoded as information. Okay, and this information Alice wants to send to Bob. Okay, and because this quantum mechanics has a non-trivial nature is there, that quantum mechanics is non-local in the aspects. Okay, which actually has been lots of discussion in this historical backgrounds is there from this state discussion from the EPR group, Einstein, Podolsky, Rosen group, to counterattack the quantum mechanics. The EPR states are discussed in the light of that, and it was realized later that no, it is the quantum mechanics is complete physics. It is not like incompleteness is there, and in fact, one has to change the
Sir, sorry to interrupt. I think your voice is not clear. I mean, you are not audible. Sir, you.
Yeah. I thought this is somehow it's muted. Now it's fine.
Okay. Yeah, now it's fine, sir.
Okay, thank you, fine. So can you tell me? I can repeat again which slide I got muted.
Yeah, this one only. This one only.
This one only. Okay, good. Okay. So this Alice lab, she wants to set up a strategy to teleport this state psi to Bob's lab using the non-locality of quantum mechanics. Okay. Quantum mechanics has a non-local structure because whatever the measurements in the Alice lab is there. Okay, if she shares somehow the EPR pair or one of the Bell states, okay, EPR state is one of the Bell states. If Alice and Bob shares this Bell states, then it is possible that Alice can transport this unknown state psi to Bob. And while teleporting this state, that means that Alice can pass any information she can encode on alpha and beta, and she can pass it to Bob without doing anything. Like if somebody disturbs this, it is like a passing to quantum channel. Okay, and in the process, like it is not like the two labs. This will be connected by the quantum channel. Okay, and in the process, this Bob state destroys to the unknown qubit. Whatever qubit Bob is sharing with Alice, that actually destroys, and Bob's qubit actually is psi. Okay, it is like that's a bit more than this transmission. In fact, whatever Bob has a particle, it actually changed into the unknown qubit. That makes this teleportation protocol a bit more interesting. And I hope most of you have gone through, but I'll quickly revisit this protocol, and then we'll pass further. Yeah, so this can be done by the circuit, quantum circuit I prepared. Okay, in fact, it is prepared by Bennett, and I'm just demonstrating it for you to understand that this is the Alice lab where Alice has unknown state psi and zero state, and Bob also has zero state, but Alice and Bob decided to make a Bell pair out of it. Okay, so when they do this action, when Bob applies Hadamard and Alice applies this gate, the C0 gate, Alice and Bob together apply C0 gate, okay, on this zero whatever bit is there, and they don't measure anywhere. Okay, they don't measure. Measurement is decided somewhere where this meter is there, where only the measurement is done. Okay, in any other parts there is no measurement is done. It just operation acts on and let it pass through any gate, let it pass through, and whenever meter is there only you measure. So Alice and Bob decided to make a Bell pair out of it, and they can do this operation. Bob will act his qubit, zero qubit on Hadamard, and followed by a control of Bob qubit to target of Alice qubit. And during this process, they will make one of the Bell states. Okay, depending on if Alice can choose 0, 1, Alice can choose 0, Bob can choose 1. They will make another set of Bell pair. If Alice uses 1, Bob uses 0, they can make with the circuit another set of, there are 4 of Bell states are there, and depending on choice of 0, 0, 0, 1, 1, 0, 1, 1, they can prepare one of the Bell states from this action. I just take this one state that they prepare a Bell state from 0, 0. Okay. Now after this action, what Alice is doing is, because Alice in her lab has 2 qubits, one that is it shares with Bob, and the other that is she intended to send it to Bob. Okay, and she will take help of this bit that she actually has sharing with Bob using local quantum operations and classical conversions. She can operate only in her lab. She has no any tool that she can operate in Bob's lab. Okay, if she could have done that, that would have been a non-local operation. But this is local operation that she can do measurements. She can apply logic. She can apply quantum gates in her lab, and sufficiently Bob can also do in her lab whatever things she want to do. Okay, they are equipped with this quantum gates. X is there with Alice, Z is there with Alice, and H is also there with Alice. And similarly, Bob also has X, Z, H. Okay, and they paired this when they met together. Then they applied this operation, C naught operation. It was not later, but when they were meeting together, when they decided that let's make a Bell pair, and then I will go to some other place, and you can be in your lab, and then you plan to send me this unknown qubit. So this is happening that this Bell pair is prepared here, and then Alice in her lab, she again applied this C naught operation, keeping the one qubit which is the unknown qubit as a target, as a control, and this the one she shares with Bob as target, and then she will pass through this one Hadamard code to the first qubit she actually has. She can name it that I have this the first qubit, that is I call it psi, unknown qubit, and the second qubit that I call it is the one which I share with Bob. And then with the naming of things, she can apply Hadamard on her first qubit. Okay, and then after that she decides to measure, and then the measurement results she can share with Bob that I got this measurement. Remember, measurement in quantum mechanics, that has a very crucial role, that measurement destroys the superposition state. Okay, before measurement there is chances of getting Alice state to be 0 or 1, 1 or 0. In fact, Alice has two qubits are there, so they can be either 0, 0 or 0, 1 or 1, 0 or 1, 1. But the moment she measures, the moment she applied this meter operation, okay, that means Alice superposition state is destroyed. Okay, and the superposition state that was together made, that was with Alice and Bob. Okay, and Alice is not doing anything on the Bob qubit, but the measurement of Alice destroys the superposition state, and what it transmits to Bob is a classical information that I got this classical bit. I got the 0, I got 1, got 0, I got 1 or 0, I got 1, 1. Okay, and this classical information, when Alice shares, Bob can do in his lab measurements, and what he found that the qubit he shared with Alice is actually a known qubit that Alice wanted to send. Okay, in the process, this EPR pair, the Bell pair that Alice and Bob created together, shared together, it was destroyed, and the particle that Bob has is actually teleported, is actually the one which was teleported by Alice as a unknown qubit. Okay, so this is a bit interesting. It was done by experiments also, later performed by experiments, not only theory, but there are sufficient evidences that this is correct. This is perfect transport is going on, teleportation is going on. We should avoid to call it transport, okay, because transport is would be something like it should get additional thing, but no, it is like teleportation. Whatever Bob actually had, it goes to psi. Okay, what Alice had in the beginning, psi, and now at the end, what Bob is actually having is psi. Bob has one qubit in his hand, Alice has two qubits in her hand, and after the measurement, the Bob's qubit is psi, and the process, the Bell pair, the measurement happened there in between, so the Bell pair that Alice and Bob shared, okay, that got destroyed. So the protocol that is going here, I wrote all this the states that you get. For example, if you apply, if the psi 1 is there, okay, it is nothing but the psi state is alpha 0 plus beta 1. Okay, then you actually have this three spins that are shared. So you have alpha 0 0 plus beta 1 0 0. Keeping in mind that first qubit and second qubit is with Alice, and the third qubit is with Bob. Okay, you can number it 0 0 as a 1 2, and this third 0 is a 3, that is with Bob. Okay, and then Alice and Bob do this prepare this EPR state, and that means that this state that is Alice and Bob, that's second and third, is going to be a pair 0 0 plus 1 1 by root 2, and similarly here 0 0 is going to 0 0 plus 1 1 by root 2. Okay, and after this APR generation, and then Alice this got psi 2, and then she applies C naught operation on her qubits, considering the first qubit that is unknown was there, applying as a control, and the second qubit as a target. So whenever it's a 1 0, it will go to 1 1, and whenever it's a 1 1, it will flip to 1 0. Okay, and this operation is there, psi 3 is there. Okay, that is followed by this operation, C naught operation, and then Alice applies a Hadamard gate on the first qubit, and she gets this state, that is psi 4 mentioned there. Okay, so at this point Alice decides to measure. Okay, so you remember this club is such a way that the first two qubits are with Alice. So in this case, in the superposition state, 0 0 is with Alice, and then alpha 0 plus beta 1, the other qubit, that is with Bob. It may be either this 0 1, alpha 1 plus beta 0. Before measurement, there are four choices are there, plus 1 by 0, 1 0, alpha 0 minus beta 1, plus 1 1, alpha 1 minus beta 0. And all of them are equally probable. All of these states are probability equal to 1 by 4. Okay, so if Alice does the measurement, the outcome will be one of these segments. She's not sure before the segment that what is there, but when she does a measurement, she will either get 0 0, 0 1, 1 0, or 1 1. Okay, the measurement will reveal her a classical number. Classical number will be 0 0. Either the spin, that is the state that is sharing, has a down spin, up spin, both are up spin. One is up, other is down, both are down, one is down, other is up. Okay, out of these four possibilities, you will get this classical number 0 0, and so we will call Bob and inform her classical number that my measurement results are 0 0. Okay, and Bob will do nothing to his qubit, and he will know that the state that I was sharing with Alice is now teleported to me as the form that I had. Okay, Bob has not to do anything, so that operation is that identity operation is there. So that is doing nothing. Okay, and if Alice result is 0 1, Alice calls Bob, informs that my qubits are 0 1. In fact, just he can say that 0 1. Okay, and Bob will understand that now I have to apply the X gate on the qubit that I have. Okay, and remember that X will make it to flip because it is alpha 1 plus beta 0. You see that the state that is Alice got when it's a 0 1, it's alpha 1 plus beta 0 with the Bob. Okay, and Bob will apply X gate, and what will happen is 1 will flip to 0 and 0 will flip to 1, and the state that Bob will be having is the one that is unknown to Alice. Similarly, Alice will doing the if she gets 1 0, Bob will do a jet operation on the qubit that he is having. It's again local operation is there in his lab, and he will retrieve back this unknown qubit that is Alice intended to share to Bob. And finally, if Alice tells Bob that results are 1 1, then Bob will understand that now I have to apply this two successive operations. Z, first we apply X, and then I apply Z. Okay, and the state that will be I am having, that will be the unknown qubit state. So that is a standard protocol given by Bennett. In fact, he showed it in later it was proved, shown by experiment also. Okay, and there are later other protocols also were developed. Okay, but this one is the kind of standard protocols. Later, people look for this optimization protocols also. Okay, and we'll concentrate on this standard protocol. We call it standard deliberation protocol. So little bit in mathematical language, we can say that this Alice and Bob, okay, when they are sharing a particle in a given state that we call this joint state of Alice and Bob, that is like EPR pair they are sharing. Okay, so when we call joint state, we have this Hilbert space dimension of Alice and Bob, Hilbert space dimension Bob. So there's a joint space is there, and the particle they are sharing is one of the state vector in this joint state, and the third particle psi, which is in some third space okay, that is not in AB, it's a third space 3 I define is, okay, is intended to be teleported by Alice using LQCC, or you can call it LOCC. Okay, it's a local quantum classical conjugation. It's the same as saying that local operation and local quantum operation and classical communication. And so we'll do this LOCC operation. Okay, let's say T some operation is doing. Okay, and to the particles that they're sharing. Okay, and in this process, okay, Alice will act this some operation T that we discussed in the previous slide, that what the T operation was there in that one, and C teleports Bob state. The final state of Bob is given by state vector, this in the density matrix rho psi this, which actually is getting by the operation that we call is partial tracing, where Bob state is partially traced third spin, that is the unknown qubit, and the Alice spin, what is Alice was sharing with Bob, that is A is there, and the remaining that is there after this protocol T applied to this LSOC protocol applied to this process of teleportation, that is T, okay, and the state that is Bob is having is rho B. Okay, so this process actually leads to a quantum channel, okay, that actually maps something what is given, it's a to an input state. Okay, input state is the unknown qubit, okay, and unknown qubit plus this joint state, and this it just converted this to Bob state. Okay, so if psi input is there, this the unknown qubit state is there, and the output is this rho psi Bob. Okay, if the channel is such that you get whatever you, for example, in this last slide that we are seeing, that the psi input psi was exactly teleported to Bob. Okay, the Bob state is exactly the psi. Okay, so that is like 100% thing is there. Okay, this channel was 100% teleporting to whatever the Alice is having to the unknown qubit to Bob. Okay, so in that case, you can say the fidelity of this. One can ask a question qualitatively, that how good the protocol is there, that you can tell in terms of a quantifier that you call a fidelity. Okay, fidelity of a teleportation protocol T. Okay, so we can define this protocol. In this case, fidelity is 1. Okay, 100% teleportation is done. Okay, however, this is not case in general. In general, we are dealing with the quite kind of the systems which are dealing with the some environment is there, some noise is there. Okay, there's a decoherence channel occurring there, and all those what makes that this fidelity of this teleportation protocol is decreasing. Okay, so we'll discuss a bit more on these aspects. Okay, before moving to the spin chains. So we define this fidelity of this channel. In fact, you can define the fidelity of a state also. Okay, what you call a channel is in fact this state also is there, because this channel gives you an output state. Okay, so either you call it the fidelity of a channel, or if you call it fidelity of the output state. Okay, you can calculate it by just projecting on the initial state. Okay, and how much it is. If you average it over all these input states, you do this. So that's the kind of optimization protocol is there. Okay, you take minimum input states and then you optimize it this quantity. Okay, and then every time you ask a question that the probability of getting the output state, okay, being the input state phi. Okay, how much is the number? Okay, it may not be all it may be like 0.5, 0.7, 0.8, 0.9, maybe some number is there. Okay, you average it over all the input states, and that you define the fidelity of a quantum channel. Okay, in fact, in general we can call it classical for a channel. Okay, later we say that why we need a quantum channel actually there. And there's other quantity is there. That's called a singlet fraction. The EPR pair that is these two guys are sharing, that is called a singlet state. Okay, I mentioned it somewhere in the beginning, but I did not took notice there that this is a singlet state. Okay, singlet state. If you do this algebra of addition of angular momentum of two spin halves, okay, you get 4 states. Out of them, there is one singlet state which has total angular momentum is 0. And there are 3 other states which has total spin angular momentum that is equal to 1. Okay, one of the triplet states, it's also a superposition state of two states, like you get psi plus also there. Psi plus you also get there. And one of the triplet states and one singularity state that you get when you add this spin momentum. We call it singularity state because it is like total spin angular momentum for this joint system is 0. Okay. And this experiment, EPR statement that was modified by David Bohm later, that let's say you have a pion is there. Pion has a spin, total spin is 0, and this pion decomposes to electron and positron. Okay, one has a spin up, other has a spin down, or maybe spin down, spin up. There's superposition state of them. Okay, so this kind of states are easily can be prepared in the laboratory, the singularity states. Okay, and the fraction, whether the information is how much fraction of singularity state is there, that we call as singlet fraction. Okay, there's another quantifier is there, and we see that these two quantifiers, the fidelity small f and the singlet fraction capital F of this channel, they are related to each other. Okay, so in this case we take a general thing for any d downside space. For spin half it is d equal to 2, and then the summation will have two terms there. Okay, and this is like 0 0 plus 1 1. Okay, which is up to a local transformation of singularity state. Okay, though what I mentioned is not a singularity state, but this is singularity state. One can do local change it to 0 1 minus 1 0 by root 2. Okay, so this state is easily to handle. That's why we are taking this one rather than 0 1 minus 1 0 by root 2. And for any channel that we define this lambda, okay, this quantity f, small f and capital F, they are related to each other. Okay, one can do the calculation. It will be like f lambda d plus 1 by d plus 1, where d is the dimension of the Hilbert space. Okay, so for a spin half case, this d is equal to 2. If you have a spin 1 case, d equal to 3. Spin 3 by 2 case, d equal to 4. Likewise, the dimensionality increases. Okay, and that will have an effect on the fidelity. Okay, so you see that because the d is lower, okay, that means fidelity will be higher in the case of lowest dimensions. Okay, for example, spin half will have a better fidelity. Okay, compared to the same protocol, same way protocol we follow for a spin system, because d plus d comes there. Okay, and you will find that f lambda is also a little bit higher, capital F lambda is higher than. Okay, so compared to two channels, if you have a spin half, spin 1, you will always find a spin half is a better candidate for this teleportation protocol. Yeah, so there's quantity to call the optimal fidelity of a channel. Okay, so when you do this, all this optimization calculations there, you average it over all the input states and find out the maximum value. Okay, this quantity is f maximum comes there in the numerator. Okay, and this is related to this small f maximum that that is we define a fidelity. Capital F is a singlet fraction. Okay, and if we test it with a classical channel, I will discuss in next slide that for a classical channel, f maximum is equal to be, capital F maximum is equal to 1 by d, that come out to be. Okay, and f maximum will come out to be 2 by d plus 1. Okay, so that just gives a limit. So for example, for a spin half case, d equal to 2, so f maximum, small f maximum is equal to 2 by 3. Okay, so best a classical channel can do is a fidelity of transmission to be 2 by 3. It's a maximum. Okay, it cannot go to more than this 2 by 3. Okay, if one can do anything more than 2 by 3 channel, then one can say that yes, so that is the advantage over the classical channel that we are having. Okay, and we'll see that in this discussion as we move on, that the channel that we'll be using, the quantum channel, okay, which will be showing a better fidelity as compared to the classical channels, the best classical channels. Okay, we always say it's the best classical channel. That is fidelity is equal to 2 by d plus 1. Okay, for more details, please visit this famous paper of Horodeckis. Okay, that's in Physical Review 1999. Yeah. So I'll just take one example, a simple example. Okay, where this example is called as this noisy singlet. Okay, because if you have p equal to 1, then 1 minus p equal to 0. and the state that you have is a you can say pure state. It's no noise there. But for any other p on other than p equal to 1, this state is a noisy state. Okay, and that has limit. Like if you put p equal to 0, then whatever this first quantity is there, psi plus that is singlet thing is there. Okay, this Bell state is there, and this becomes 0, and you get a complete noise zone. So for p equal to 1, the fidelity, we know that the standard protocol of this guy Bennett protocol, that is giving you f equal to 1. That's a perfect deliberation is there, and capital F is also equal to 1. Okay, but if p is not equal to 1, if p equal to 0, the other limit is there. There's a complete random noise is there. There's nothing like a pure state there. A complete random state is there, and if you average it over the states that Bob is getting, you try to optimize this here. Okay, so in the fidelity expression, you see that the expectation value is there, and if this is random, okay, you are tracing out over the random degree of freedoms. Lambda goes to random. Your all the outcome that is going random. Okay, and the dimension is the d dimension of this there. Okay, so what you get actually is this reduces to 1 by d. Small f comes out to be 1 by d, and capital F comes out to be 1 by d square for a complete random state, complete random noise. Okay, random matrix theory guys, they will be very easily happy to do this for us. Okay, whenever they define this thing, that let's take a random noise there, then we just apply random matrix theory, and we see that what is the result is there, because everything averages out. Okay, and the dimension comes there because there's an identity cross identity. Nothing applies on this A or B part. Okay, and result is f is equal to 1 by d square. Okay, so there are two limits we can get for this noisy singlet. That one limit is for f is 1 by d, okay, when p equal to 0, and f is equal to 1 when p equal to 1, and everything that are in between this thing. Okay, so we can just write this f in section f is equal to p plus minus p by d. You put the value of p that is there, and what is the purity of this single state is there. You put it here, and you get the fidelity. And similarly, one can get capital F also, the same fraction there. Okay, again you can put what is the purity of this state is there. That purity you put it here, and you get this quantity capital F. And they are related. The lesson that I wrote in the last slide, you can find it here also. F equal to fd plus 1 by d plus 1. Okay, so fd plus 1 by d plus 1 is there. Okay, so there's a criteria is there. It's not in this paper, theoretical paper, it's in the paper. It's given that this state rho p is separable for a limit of values of p. If p is less than or equal to 1 by d plus 1, okay, and greater than 0, okay, this state remains separable. Okay, that is, there is no entanglement involved. Okay, if there is an entanglement is there, then that is beyond this p equal to 1 by d plus 1. Okay, to p equal to 1, because singlet is sitting there. It's a maximum integrality psi plus state is there. Okay, and the entanglement increases, okay, when you are going beyond p equal to 1 by d plus 1. Okay, and this gives a criteria for a classical, because when you say that rho is separable, it is usually called as a classical system. Okay, classical system doesn't mean that you are dealing with a classical mechanics, but it's a classical state. For example, this up state, both spins are up, that is like a classical state. Okay, and for a classical state, if you want, one can do the calculation. Okay, and we get a limit. The maximum is 1 by d and minimum is 1 by d square. Okay, for the capital F, the single fraction is okay, and maximum is 2 by d plus 1 for fidelity, and minimum is 1 by d. Okay, so one can see that the limit, that is maximum small f can be there. For spin half that has d equal to 2 is 2 by 3 here, and the minimum will be 1 by 2. A classical channel will have anything between 0.5 to 0.6. Sorry, 0.66. Okay. Anything which is beyond this, whether it is attainable, okay, that quantum mechanics will help us. Okay. We take another example. And this example is an arbitrary state of a 2-qubit system. Okay, one can prepare this two-bit system, okay, where you see that the identities are there, okay. Then you see that this r dot sigma kind of this is the first first qubit space, if you call it the Alice space is here and Bob space is here. So this is the, and then identity I cross this with the Bob states is there, and then you have this interaction term between this Alice and Bob states. Okay, so this is a most general two-qubit state. Okay, the nomination comes there with the condition that trace of rho square is equal to 1, trace of rho equal to 1. Okay, from that condition we can get rho equal to 1 by 4, and this T mn, that is this kind of it's coefficients of this matrix T. Okay, Tmn one can get. Okay, and there's always a chance to this state is there. You can always apply some local rotations u1, u2, u1 plus u2, one on the Alice side and 2 on the Bob side. Okay, and we can rotate this state, the joint state. Okay, and by applying local operations. Okay, in such a way that this T matrix becomes diagonal. Okay, in this other sense, it's called a diagonalization of this T matrix. Okay, and this is done by you can define this some O1 this Euclidean rotation there for this R vector, and Euclidean rotation for the S vector, and that becomes in fact this rotation of the T vector will be like Euclidean 1 and Euclidean 2 acting on this T. Okay, and one can rotate in such a way that you have a T matrix that is diagonal. There are no optimal terms there. You rotate in such a way. Okay, and after doing this, one can calculate the fidelity of the system. Okay, that will come out to be 1 by 4 plus summation right Tii. There is exact expression there, and this condition is that the determinant of T should be negative. Okay, and if determinant of T is positive, in that case you get this expression. Okay. So this also like one can expand this state. It's a arbitrary two-qubit system. One can expand this state space. One can go to higher dimensions for 3-qubit space, 4-qubit space. Okay, and one can do calculation again for fidelity. Okay, and one can find, you can plot those things. Okay, details you can find in this paper. This is another paper of Horoteki with Bajiak et al. Bajiak, Horoteki. Yeah. Okay, so that's a basic of this teleportation. Okay, I'm sure that's not so much basic, but because I had a sense that it's an advanced level FDP is there, so I wanted to respect this advancement of this FDP level. So little bit mathematics and because a little bouncers are there. Okay, so but you try to understand, and in the textbooks things will be very much clear there. So the another this aspect, the main aspect that for this talk is the spin chains. Okay, and it is regarded as they can serve as a quantum wires for a quantum computer. Okay, they can transfer the states from one end to another end of this chain. Okay, they can do lots of tasks for us. Okay, the spin chain is like your spin halves. They are sitting on a lattice. Okay, for example, here we have one dimensional lattice. Okay, and the lattice points. I try to draw the atoms. Okay, and I don't know what it became, but you understand that the atom is there, and there is a spin orientation is there. Probably there is a 1 electron is there. If you want to take a spin half, it's 1 electron is there, and that is the conduction electron is there, and other valence electrons are so much immobile that they cannot contribute you to the spin angular momentum. The whole angular momentum of this electron is from the spin half. Okay, so if we have this thing, this channel is this whatever system is there, and there is an interaction between the spins that is taken into account. Okay, and let's say J is the interaction. So we can define a term like JSI dot SJ, kind of the interaction between two spins, spin interaction. Okay. On top of that, the system will have also a negative field. Okay, so these spins are actually like one of these not only after this electronic spins, okay, but even this when the spin concept came there, okay, lots of work were going on. Okay, lots of understanding, because this is a very simple model of a very complex system. Okay, a many-body system is a very complex system. Okay, one has to find out lots of work there to understand a many-body system. Okay, In fact, if your 3-body system is there and somebody asks you to solve exactly, you'll find that there's a lots of trouble is there. But spin system poses a problem on the understanding of a many-body system where you have interactions between this bodies there, okay, and one can understand the dynamics of the interaction. Okay. So there are famous models there. I can write this if I have like a spin system is there, a chain is there, and I apply a magnetic field H there on this system, okay. And this is a general Hamiltonian of the system that you call. Hamiltonian defines as the total energetics of the system, okay, which a system can follow. And this model has been like the history side. If you go for that, lots of work going on, lots of Bethe involved there, Ising involved there, okay, Leib, Schulz, Matisse, Onsager, Young, C and Young involved there, Boxster involved there, lots of guys involved there to solve, to get the exact model. Exact model is the one where you have an exact eigenvalues and exact eigenstates for the model. Okay, the way you solve it, it is not always you get the exact model. There are very few models in quantum mechanics where you can exactly solve, because there are very few many-body models there which can be exactly solvable. Okay, so but these are few models which actually are exactly solvable. Okay, and exact solution gives us a hint that we can go for n is equal to infinite. Whatever this number of lattice sites you want to take, you can take, and you can work it out calculation, and you can test it in a thermodynamic limit. So this is one model is there where you have Jz is non-zero, Jx is equal to 0, Jy equal to 0. You put there, and this is called a longitudinal Ising model. Okay, this was discussed in the early 1920s by Ising himself. Okay, who was a student of Lanzmann, and the 2D model of this system is very difficult, was solved later in some 20 years after by Lance Onsager. Okay, and 3D model was given a solution by Young, and so that's again non-trivial things are there. Okay, this we are just discussing the 1D models there. Okay, 2D models are a bit difficult there, and this x-axis model is there, that is solved by Bethe. Okay, there's a famous Bethe theory is there. Okay, and Bethe and Saz, algebraic Bethe and Saz, that gives a solution for this model. And then there's a xy model is there when Jx is equal to Jy, Jx is not equal to Jy, and Jz is equal to 0. That model is xy model, and that was solved exactly in 1961 by Lipschitz Matisse using Jordan-Wigner transformation. Okay, and the same class of model is a transverse Ising model where you have Jx is non-zero and Jy, Jz are 0. That's a transverse Ising model which is in the same class as xy model and can also be solved using Jordan-Wigner transformation. Okay, and the first one given by Lipschitz Matisse. Okay. And then you have XXN model that was solved in 58 by Orbach, and then Baxter solved the XY model, which is non-trivial model, which is Baxter's solution, which was worked out with the inverse quantum scattering methods. And that's we don't want to discuss these things. Okay, the model is there, that should be there, and the task that is there in our hand is teleport the state using this the spin setup. Okay, and this teleportation is done by the spin chain. Okay, so Alice and Bob are related, are joined by this quantum channel that is between them, that is spin chain between them, and this channel will Alice and Bob sitting on this channel, they can, whenever they wish, they can create this singlet state, they can share among them the API state. Okay, and they can check, because this is the key to this teleportation, this sharing of the singlet pair, singlet state. So Alice can which is sitting here, and she can encode this Bell state, prepare and Bell encode this state, and she can transmit. Maybe one in Bob is there. Okay, so that's the channel is there. Okay, so receiver is Bob and sender is Alice, and channel is the spin chain. Okay, so in the beginning we initialize this chain. That means we take all the spins up in the 0,0 state, and let's say you have n such spins are there, and they all are in 0 state, and then you pick you pick in the center of this one, this n by 2 and n by 2 minus 1 and n plus 1 is there. So you just take n by 2 and n by 2 plus 1 and make a bell pair. You have to apply a Hadamard gate followed by a CNOT gate, okay, that will encode a bell state at the center. Okay, so we have done this analysis for a system, various kind of systems. Okay, and like here, the main conclusion would be no matter what is the spin model you are taking. Okay, if it is, let's say, general model H model is there, whatever the understanding will be there, okay, that will be applicable for all the systems, provided they have a condition that is the total magnetization of this system is conserved quantity. So when we encode this at the center, okay, and this encoding with the help of this Hadamard and CNOT gate, and then we look for this sharing protocol. Okay, so this is the initial state, and at time t equal to 0, we encode this omega 0 0, we call it bell state, and this encoding makes it 0 0 plus the whatever this site is n by 2 plus 1 is a flipping is there. Okay, so this is a supersession of all up and all up except 2 flipped. 2 flipped are n by 2 plus 1 at the center where the flipping is then there. Okay, so because this is the super state, the first is 0 0. Okay, so it will contribute in the all up state, and the second is 1 1, which is sitting 1 here at n by 2, and other one is n by 2 plus 1. So that will contribute in the second superposition state. We just denote it by n by 2 plus 1. It means that others are 0 except n by 2 plus 1 is 1. Okay, and details of this work is in quantum mechanical processing general. Okay, that we published last year. And so if you do this time evolution of this state, okay, time evolution is done by this because you have Hamiltonian is there. Okay, and Hamiltonian is a generator of time transition in quantum mechanics. Okay, you will always have this evolution operator, this e power minus I st by h bar if the Hamiltonian is time independent. Okay, and you can apply it on this state, the initial state, and you can get the time transitive state. Okay, so we have the g notation is there, that is e power minus st there, and one can calculate this g because of this liberty that the space this state is there, that is all two spins flipped at the center, and because the magnetization is conserved quantity, no matter how long you do the evolution, okay, you will always be in a two-state flip state, no matter whether it may not be at the centers, but it may distribute somewhere there. Okay, but it will always be two acceptance states there because magnetization is a conserved quantity. Okay, and then with this we can define this the input state as a psi t, and we can do our measurements there. We can do we send it to state and let Bob to find this the state. Okay, the Bob state will be the tracing done over all the states except the one which is the endpoints 1 and n. Okay, and what we find is the equations that we don't want to bother you to look into it. Okay, but this is expression, and when we define this input state, okay, that is omega 0 0, and we can calculate psi, this singlet fraction, which is very easily can be calculated there, and this help us to look for variety of models. Okay, what a singlet fraction will be in those models. Okay, ranging from XXZ, XX model. Okay, there are some KIG models there, and when we optimize it, we do it, average it for many input states, and the optimization tells us that there are a few models which actually are giving us way ahead than the maximum, the best a classical computation classical channel could give. For example, the value here you see that x 0.703 comes there. The value for this model that we had not yet discussed much this today, but discussion is there in the paper. Okay, that is giving you maximum 0.7552 you can get. Okay, which is beyond this other models there. Okay, and though you have to apply some kicking scheme, you have to continuously do the periodic kicks to the system, and we can calculate these things. Okay, so with this, I just summarized what we discussed today. Okay, we discussed this qubit, gates, we discussed standard, this protocol, this teleportation protocol there, and we discussed this quantum channels there. Okay, the qualitative analysis of the fidelity and singlet fractions. Okay, we also discussed this spin chain as a quantum channel there, and explored in fact various models. We had not much time to discuss all the models. Okay, but in general, like we can do this analysis for any model given the Hamiltonian is known to you, and the condition is that the Hamiltonian is meant as a conserved quantity. One can check this as a channel whether this is the optimally channelized, the optimally fidelity and singlet fraction, whether it's more than classical channel or not. Okay, if it is more than classical channel, then it is a utilizing aspect of the system. And if it can be easily prepared in lab, then definitely it's a wonderful thing for us. For example, this system, lithium cuprate, okay, it's a good system to do in the preparation lab, and with the parameters they have, okay, one can model it and one can use them as a teleportation protocol, this channel for us. Okay. So thank you all of you, and I think I finished within time. And my voice is still audible to you. Is it? Is it audible to you? Yes.
Yes, sir.
Yeah, sir.
Yes, yes. There's a question by, let me read a question by Anindita Sarkar. If we use teleportation in a cryptography, will it increase complexity? In fact, teleportation is if you go through the Eckhart's method, okay, they are using this teleportation protocol, okay, and it is not using complexities. Yes, definitely it's a good the protocol, okay, but the longer run to share to based on this it's a EPR production is there. You have to always produce EPR pairs, okay. So in the cryptography, it's better to have some other methods. For example, this BB84 protocol is there, where you can just you don't involve in generating this EPR states, but you can just toss the coin, generate this random states, this random sequence of coins, okay, random bits, and generate on that random bits. You generate the basis, choose the basis, and choose the state, okay, and then ask the other party, okay, to send it some numbers there, okay, and if they are using the same basis, okay, because there is uncertainty is there that whether it's a plus X is there or plus Z is there. So the uncertainty is there. That uncertainty is in the mind of the eavesdropper is there, and one cannot detect. If try to detect, one can find that where it's detected. Okay, so definitely it's a better than this protocol, this teleportation protocol, because the complexity is reduced in that protocol. Okay, because generation production of EPR pairs is a bit difficult task there, and they have to always be in a channel to produce this EPR pair. Okay, so other option, other question is there any basic level book for beginners? Yes, definitely. Please go for this Nielsen and Chuang, Basics of Quantum Computing. Okay, this is a wonderful book. Okay, one whether a beginner or whether expert, okay, they should always carry these things. And there's a new book by this guy Mark Wilde. Okay, please you can refer to this book also. Okay, they are very good book for beginners in this direction. Okay, and thank you. I think I got some appreciations for colleagues. Yeah. Okay. So is there any question?
Yeah. Thank you very much, sir, for your wonderful session. You take all the trouble to take this session out of your valuable times. So thank you very much, and we hope to hear from you again in the near future.
Yeah, sure. And if anyone has